Your FastMCP server is wide open to abuse. Any client could flood it with thousands of requests per second, and you wouldn't even know until your server crashes under the load. We'll implement 2 production-grade rate-limiting strategies: a token bucket system that allows controlled bursts of traffic, and a sliding window approach for precise, time-based request throttling. You'll see exactly how to configure both to protect your server while keeping legitimate usage smooth. From FastMCP server middleware rate limiting import. Rate limiting middleware. Sliding window rate limiting middleware. Hash token bucket rate limiting allows controlled bursts. MCP add middleware rate limiting middleware. Max requests per second equals 10, 0. Burst capacity equals 20. Hash sliding window rate limiting, precise time-based control. MCP add, middleware sliding window rate limiting middleware. Max requests equals 100. Window minutes equals 1. This demonstrates the middleware pipeline pattern for cross-cutting concerns in RPC systems. Rate-limiting middleware intercepts requests before they reach your core logic, applying usage constraints without modifying your business code. The distinctive aspect is the declarative composition. You add middleware layers to the server, and each layer handles a specific concern like rate limiting, logging, or authentication. The pattern works through a chain of responsibility design. Each middleware processes the request, optionally modifies it, then delegates to the next layer via call next. This creates a clean separation where infrastructure concerns, like rate limiting, remain isolated from your tool implementations, while still having full access to the request context. The order of middleware addition defines the processing sequence, enabling precise control over when constraints are applied. This approach solves the problem of scattering infrastructure code throughout your application. Instead of embedding rate checks in every tool, you centralize the logic in reusable middleware components. It's particularly valuable for multi-tenant systems, public APIs, or any scenario requiring consistent policy enforcement across many endpoints. The trade-off is slightly increased complexity in debugging request flows, but the benefits in maintainability and consistency outweigh this cost. Let's break it down line by line. From FastMCP server middleware rate limiting import. This imports rate limiting middleware classes from FastMCP's server middleware system. These handle request throttling to prevent abuse and ensure fair resource allocation. Rate limiting middleware. Rate limiting middleware implements the token bucket algorithm for rate limiting. It allows controlled request bursts while enforcing a sustained request rate, preventing API abuse without sacrificing responsiveness during temporary spikes. This is the standard pattern for protecting FastMCP endpoints from flooding attacks. Sliding window rate limiting middleware. Sliding window rate limiting enforces precise time-based request quotas. Unlike fixed windows that reset at intervals, this tracks requests across a moving timeframe, preventing burst attacks while maintaining consistent throughput. Critical for APIs where timing manipulation could defeat simpler rate limiters. This closing parenthesis terminates the middleware configuration block, finalizing the rate limiting setup for the MCP server. It ensures both the token bucket and sliding window limiters are properly registered before the server starts handling requests. Hash token bucket rate limiting allows controlled bursts. MCP add middleware rate limiting middleware. This enables token bucket rate limiting, a strategy that allows controlled bursts of traffic while maintaining an average request rate. The middleware enforces a maximum sustained rate of 10 requests per second, but permits short bursts up to 20 requests, preventing strict throttling during temporary spikes. Max requests per second equals 10, 0. sets the sustained request rate to 10 requests per second. This establishes the baseline throughput while the burst capacity handles temporary spikes, preventing server overload during normal operation. Burst capacity equals 20. This defines the token bucket's burst capacity, allowing 20 requests above the normal rate limit when needed. It handles traffic spikes gracefully while maintaining the 10 requests second average, preventing strict throttling during temporary bursts. The combination of rate and burst capacity implements the token bucket algorithm for controlled burst handling. This closes both middleware configurations, finalizing their registration with the MCP server. Each closing parenthesis terminates a distinct rate-limiting strategy, enabling both burst handling and precise time-based control to work simultaneously. Hash sliding window rate limiting, precise time-based control. MCP add, middleware sliding window rate limiting middleware. This implements sliding window rate limiting, a precise time-based approach that tracks requests within a moving time window. Unlike fixed windows, it prevents burst attacks at window boundaries by smoothly enforcing limits across any time interval. Critical for APIs where consistent request pacing matters more than allowing occasional bursts. Max requests equals 100. Sets the maximum allowed requests within the sliding window period. This hard limit of 100 requests per minute prevents API abuse while maintaining predictable throughput, a critical defense against denial of service attacks. The sliding window algorithm enforces this consistently across all clients. Window minutes equals 1. Defines the sliding window duration as 1 minute. This time window determines how requests are grouped for rate limiting, ensuring the max requests limit applies to any 60-second period rather than a fixed interval. Prevents burst attacks while maintaining consistent throughput control. Closing parenthesis for both middleware configurations. This finalizes the rate limiting setup, ensuring the server enforces both burst capacity and sustained request limits before processing any incoming calls. Rate limiting patterns. The token bucket and sliding window implementations in FastMCP 2 demonstrate how different algorithms solve the same problem with distinct trade-offs, where token buckets allow bursts while sliding windows enforce strict time-based precision. Burst capacity values must be at least as large as your max requests per second to avoid unintended throttling during normal operation. Choose sliding windows when you need precise compliance with time-based quotas, and token buckets when you want to accommodate temporary spikes.
The limit that never moves becomes the window through which all requests must pass.